All right, so we've talked about the derivative. Now we're going to talk about the second basic concept of calculus using the same example. What you'll notice immediately is that I've got a similar xy axis, but while the x-axis is still the same time in hours, the y-axis, now we want to talk about it as being speed. And so if you think back to that first example of travel, since you were traveling at 60 miles per hour for the entire 3-hour trip, we can represent your travel on this graph as a flat line that is at 60 miles per hour. This is a function, it's just a rather boring one. It simply says that you were traveling at 60 miles per hour the entire time. And if you want to calculate the distance that you travel, you think back to elementary school where you learned that distance is rate times time. Now that only applies, of course, when the rate is constant. But lucky us, that works in this situation since we were driving at the same speed the entire time. So we take the rate, which was 60 miles per hour, we multiply by the time, which was 3 hours, and we get 180 miles. Notice that the units cancel out just right. We have miles per hour, we're multiplying by hours, and so what we're left with is miles. Now, there's something else that's useful to notice, and that is this, on this particular graph, we can form a rectangle that is 3 hours wide and 60 miles an hour tall. The area of that rectangle is just its height times its width, which in this case is 180 miles. Now I know it's a little odd to think about area as being in miles, but for this particular graph, given the units on the y and the x-axis, the area underneath this simple function is in fact in units of miles. And it does represent how far we have traveled. Let's go to that second example, and maybe it'll start to be a little more clear why I'm emphasizing that bit about the area. Well, recall that in the second example, you drove at 30 miles an hour for the first hour, then you drove at 60 miles an hour for the second hour, and finally at 90 miles an hour for the third hour. Now, remember, the distance traveled is only the rate times the time if the rate is constant. But what we can do here is break up our travel into 3 separate hours, and then our speed for that hour is constant. And so it forms 3 little rectangles, like this, that break up the function. All we do is we multiply the rate during hour 1 times the time during hour 1. Then we add the rate during hour 2 times the time during hour 2. Then we add the rate during hour 3 and multiply it by the time during hour 3. In that first hour, this rectangle takes up an area, if you'll allow the term, of 30 miles. This second hour, the rectangle takes up an area of 60 miles, and in the third hour, we take up an area of 90 miles. Add them all up, we've traveled 180 miles. All right, let's get to the real example. Now here we have the most complicated motion. We started out going pretty fast, and then we stopped at Wendy's, so our speed goes down to 0. We're just marking time here. Then we take off, and then we decide to take a what we thought was a shortcut, but in fact proves pretty bad. So what happens to our speed during part of this shortcut? Well, it becomes negative. What does that mean? It means that we're actually heading back towards our house rather than forward towards our grandmother's. When we finally realize our mistake, we have to go at some mega galactic speed to try to catch up. And so that blue graph tells us how our speed varied throughout the entire 3-hour trip. But we can still, even though the curve is much more complicated, we can still in principle break it down into a bunch of little rectangles where the rate was constant for that little amount of time. And so it's rate 1 times time 1 plus rate 2 times time 2, all the way through until we've done all k, let's say, of these rectangles, rate k times time k. And we should get the same result. We just have added up all of those rectangles. It should give us the distance traveled. And in fact, it does. But notice that we can get really fancy in our notation here. And we can write this sum of all those rectangles using the sigma notation. Namely, a sum from I equals 1 to k of the rate at a particular time times how much time we spent traveling at that rate. Well, in fact, when you take the limit as each little time interval becomes smaller and smaller, in the limit that those time intervals go to 0, you introduce a new notation known as integral notation. And it tells you that the total distance that you've traveled is simply the sum of all those tiny, tiny sliced rectangles. And it does in fact come to 180 miles. And so what we see from each of these successively more refined examples is that the idea of the integral is simply the area under the curve. Now, as with the derivative, we'll spend half the year talking about when integrals actually exist, what they're useful for, how we can derive them, what formulas there are for integrals. But if you can just remember through this entire class that the derivative is the slope, the instantaneous slope at a point, and that the integral is the area under the curve, then you'll have the conceptual framework of calculus down.